So in this video we're going to find the surface area of a surface of revolution when the surface is being revolved around the x-axis. And it's going to be a little bit longer video because what we're going to do is solve this two different ways to show you that you have flexibility in terms of how you set up the integrals. But what we are also going to see is that one way is going to be probably less difficult than the other and require less mental gymnastics to do. So here we go. So again, it's going to be a little bit lengthy, and I apologize for that. So find the area of the surface formed by revolving the graph f of x equal x squared about the y-axis on the interval from x. X is the closed interval going from 0 to square root of 2. We're letting x run over that interval. And this for the first example, we're going to do dy slices for our integral. That's going to be how we do the first interval. The second, we're going to then go to the next screen, and we're going to do the next one using dx slices. What you're going to see is that in this case, dx slices will be easier, although sometimes dy slices are easier. So we need to understand that we have two different ways that we can set these integrals up. So let's start by drawing a quick picture. We have f of x equal x squared on the interval from 0 to square root of 2. So we're going, we have a parabola. We don't care about the left side of the parabola because we are only working in quadrant 1 here. So we've got this guy, he's going over to the square root of 2. So this ordered pair where we land, input square root of 2. If we input square root of 2 for x, we get square root of 2 squared is just 2. So on the y-axis, it's going from 0 to 2. So if x is running from 0 to square root of 2, y is running from 0 to positive 2. Y is running over that interval. So one option we have here is to do some dy slices. So if we think about the radii, if we're rotating around the y-axis, so doing a y-axis rotation, the radii right here of the frustrums, when we're rotating them, it's given by the x-coordinate. So we know that y equals x squared, which also means that the square root of y equals x in quadrant 1. So the radii here, the x-coordinate, which is the radius going from the y-axis out to the curve, can be described either as a function of x or a function of y. It can be described as a function of x or a function of y, depending on what we want to do. So remember, surface area of revolution is equal to, we can do 2 pi. And if we decide to run the interval along the y-axis instead of the x-axis, that means we're doing dy slices. So we would need to have the radius as a function of y if we want to run it along the y-axis from 0 to 2. And then it would be the square root. We have the arc length. It's 2 pi times radius times the arc length formula. So 1 plus, and if we're running along the y-axis, it's going to be f prime of y squared, or remember, x prime is f prime of y. So, and then we have to close this off. This is because we're doing it with respect to y. These are dy slices. So here's the integral that we would need to calculate. So we can start to substitute some pieces in. We can say, hey, this is 2 pi times the integral from 0 to 2. The radius as a function of y is going to be the square root of y. The distance from here to the curve, this distance is x. But x is also the square root of y. So I could substitute square root of y in here. And then I'm going to have the square root of some stuff, dy. And we probably want to do what we've been doing all along, where we clean the stuff up under the radical before we plug it into the radical. So f prime is x prime. So I solved for x. So x prime is just going to be the derivative of this, which is going to be 1/2, because the square root of y is the same as y to the 1/2. It's going to be 1/2 y to the, subtract 1 from 1/2, we get negative 1/2. And then this says square the derivative, so we would square both sides. And if we do that, we get a quarter. And we get negative 1/2 times 2 is negative 1. So we get y to the negative 1 equals x prime squared. And then we know we need to add 1 to it. So it's going to be plus 1 or 1 plus. We add 1 to both sides. And this is what needs to go under the radical. And this can probably be cleaned up a little bit. This is the same as 1 plus y to the negative 1. We can send the y down into the denominator as long as we make it 4y to the positive 1. And if we found a common denominator, we could add these, so we could change 1 into 4 over y. 4y over 4y is 1, and that would give us 4y plus 1 all over 4y as the thing we would be cramming in here. So we get 1 plus 4y over 4y. And then we can do some simplifying here. So here's what I can see. I can see that this piece right here, 4y is the same as 2 times the square root of y squared, as long as the y's aren't negative, which they aren't on this interval. So I can replace this with 2 square root of y squared. And if we take the square root of 2 square root of y squared, we'll get a 2 coming out. And the square root of y squared would have a square root of y coming out. So we could get this to simplify to pi times the interval from 0 to 2 of the square root of 1 plus 4y dy. And then we can integrate this. So if I'm going to integrate this, I want to recognize that 1 plus 4y is really the square root of that is really 1 plus 4y to the half. So my guess, if I integrate this, would be to take the 1 plus 4y, and we would need this exponent to be 1 bigger because we're integrating. And then when we take the derivative of this, we need to get this back. So if I took the derivative of 1 plus 4y to the 3/2, the 3/2 would come down, and there's no 3/2 here, so I would need to kill that 3/2 times, we would get the derivative of the inside by the chain rule, so I'd be times another 4, so I need a 4th to kill the 4 that would come out. So 2/3 times a 4th is going to be 1 over 6. So my antiderivative is going to be a 1/6 of 1 plus 4y to the 3/2 power, and this is going to be from 0 to 2. And again, the way you check to make sure this antiderivative is correct is you take its derivative and you make sure you get back what you started with. And this 1/6 is a constant, so I can just factor him out front. And now I can substitute my pieces in. So I get pi over 6 times, put the 2 in for y. We get 2 times 4 is 8, plus 1 is 9, and 9 will be to the 3/2 power. Minus, now plug the 0 in, we get 0 times 4 is 0, 0 plus 1 is 1, 1 to the 3/2. So we get s equals 9, it's going to be pi over 6, but 9 to the 3/2, this 2 is in the bottom, so it's the square root of 9 is 3, and 3 cubed is 27, minus 1 to the 3/2 is just 1, so we get 27 minus 1 is 26 pi over 6, which reduces to 13 pi over 2 goes into there 3 times. We get 13 pi over 3 as the surface area. And this was taking dy slices. And what you can notice when you took dy slices is we had to get kind of clever as we moved through this middle section to get it into a form that was easy to integrate. So what we want to do is calculate the same surface area, but instead of using dy slices for our y-axis revolution, let's use dx slices instead. So the picture I get is the same. On the interval from 0 to the square root of 2, I only care about this part of the parabola. He's going to the square root of 2. This is still going to be square root of 2 comma 2. And the key is, when I am doing the y-axis revolution and I pull my radii out from the y-axis to my curve, these are just the x-coordinates. The x-coordinates along here give me my radii, the distance from the y-axis to the curve. So if I set up my surface area interval, which is 2 pi, times the integral, I can run it from 0 to the square root of 2 if I want to run it with respect to the x-axis using dx slices. And we know it's going to be the radius now. If I'm doing dx slices, it has to be the radius as a function of x times the square root of 1 plus, and now if I'm doing dx slices, my length, my arc length, is given by f prime of x squared and dx. So I can do this using dx slices instead of dy slices. So let's see how this works out doing it this way. So we can start to make some substitutions. I can say this is 2 pi times the integral from 0 to the square root of 2. My radius as a function of x now is just the x-coordinate, whereas in the previous example, because x was the radius, I had to use the square root of y because I was doing dy slices. So I got something more complicated in that position. Here I'm just going to get x times the square root of some stuff dx. I probably still want to clean this up a little bit, but now I can just take the derivative of f of x. So f of x equals x squared means my f prime is equal to 2x, and I know I need to square the derivative. So we'll do that. And then if we square the derivative, so if we have f prime squared sitting here, this is going to be 4x squared. And we know we need to add 1 to the square of the derivative. So we'd be adding 1 to both sides of this. And that makes this the thing that needs to go under the radical sign, this 4x squared plus 1. And right away what is noticeable, if I give myself some room here to work, is that the derivative of the expression under the radical sign is almost what's sitting right here. The derivative of 4x squared plus 1 is 8x, which only differs from x by a scalar, which tells me that u substitution is one way to attack this. So I can say, hey, I'm going to let u equal 4x squared plus 1, which means du dx is just equal to 8x. The derivative of 4x squared is 8x. And now multiply both sides by an eighth and multiply both sides by dx. We get an eighth du equals x dx. I can replace x dx with an eighth of du. So we'll go down and make that replacement. I get 2 pi times the integral. X dx gets replaced with an eighth of a dx. But this 1/8, because it's a constant, can be factored out in front of the integral. And 2 will go into that 8 4 times. So I've got my dx sitting here. And the substitution that we made was to take the stuff under the radical sign and replace it with u. And then what we can do is change the bounds of integration. So when x is 0, right here, we put 0 in for x, we get 0 squared is 0 times 4 is 0 plus 1 is 1. U is 1 when x is 0. And if we replace the upper bound of integration, the square root of 2, when x is the square root of 2, we get square root of 2 squared is 2. 2 times 4 is 8. 8 plus 1 is 9. U is equal to 9 when x is equal to the square root of 2. And now we're ready to do our integration. So we're going to integrate. We get pi over 4 times the square root of u is really u to the 1/2 power. So our guess is going to be to increase the exponent by 1. So 1/2 plus 1 is 3/2. But when we take the derivative of this, we need to get u to the 1/2. So I'm going to need to multiply by 2/3 here, because 3/2 times 2/3 is 1. And we're going to be taking this from 1 to 9. This is a constant, so I can multiply 2/3 times pi over 4 right here. 2/3 times pi over 4 is going to equal pi over 6 times, we put the 9 in for the u, so we get 9 to the 3/2 minus 1 goes in for u, 1 to the 3/2. So we're going to get the surface area is equal to, we have the pi over 6, and now things are playing out just like they did on the previous slide. We get the 2 in the denominator says take the square root of 9 is 3. 3 cubed is 27, minus 1 to the 3/2 is 1. 27 minus 1 is 26 times the pi over 6 reduces to 13 pi over 3. So what we see is that we get the same result whether we take dy slices, 13 pi over 3, or dx slices to get at things. The issue is probably that in this particular case, the dy slices were more difficult to think about and to work through without making a mistake than the dx slices were. So in general, my comment would be, it is relevant to think about when you're working on both arc length problems and surface areas of revolution to think about how the integrals would play out if you took dx slices versus dy slices, because in both cases, regardless whether you're working with respect to the x or the y axes, you have two options for setting up your integrals. Sometimes one of the two options will be possible, whereas the other is possible to do into a closed form. And sometimes both will be possible, but one will just be much simpler than is the other.